Thank you. All the time, my field is all the time totally real field. I can do any field, but then you don't have Shimura variety, and you can't say about Tate conjecture. So therefore, I assume that it is totally real. So I take a quaternion algebra B that produces a Shimura variety. Its dimension is twice R positive, and that is B is a quaternion algebra over E, and to have a similar subvariety of appropriate dimension, I mean dimension R inside this, I need to assume that this E contains a subfield F of quadratic extension of another totally real field F. There could be many F's, but anyway, I assume that. And then I have, I want to have a quaternion algebra D over F. And to put this guy inside B, I suppose that B is just a D tensor Fe. And so this is the setting. And therefore, Shimura variety of this one contains SHD. Okay? And I assume that this D is division. B can be split, but this is division. Long ago, I did basically same sort of thing for Hilbert modular variety. So B and D both M2 matrix algebra. That 1999 paper, similar thing I did. Then I become so busy about universal theory, I took 10 years to prove mu invariant vanishing. I thought at that time I do this business for Hilbert modular. Then they Getz pick up this, and he proved sort of Tate conjecture in a very weak form. Anyway, so I need to do quaternions, so I started doing that. Okay? So I consider therefore I fix applied. And I consider H twice R of SHP of QL twisted by R times this dimension, half dimension. And then you take invariant subspace, Galois of Q bar over X. X is a finite extension of over Q, but it has to contain the reflex field of SHB, the natural field of definition of SHB. And this is the space of Tate cycles. And conjecture is that this Tate cycle is spanned by algebraic cycles, defined by this X. And by doing this business is that it's a sort of explicit version of Tate conjecture. That means I really wanted to know what cycle span the space. That's the important point, not something somewhere. So, as you know, that the this H to R, this is a dark homology, and B could be split. I put cusp here. B could be 2 by 2. Otherwise, it's just a compact. I don't really much need to do that. And these cohomology are eternal cohomology. So actually, I need to tensor. This is actually SHB over its reflex field to Q bar or something. And then I take the eternal cohomology. Okay? And then this by Lagrange. So all the time I forget to put the cusp, but it has to be cusp. And so this SHB to error, you can decompose it over automorphic representations pi discrete series, homomorphic discrete series of weights 2 on this quaternion algebra. And then you have two actions, Galois action and Hecke action. This is Hecke. This is Galois. And this dimension of big pi is 2 to the 2r. Okay? And so because Hecke action and Galois action commute, so you can split into this way. And this pi appears once, but of course this guy may have factors in it. They have multiplicity kind of things. And what I want to do is that out of B, I call D sigma. So this is quadratic extension, it's a Galois. This is generated by one element sigma. And of course, this Galois group acts on this factor E, therefore it acts on B. So I define D sigma to be just B in B, such that B main involution is equal to B this Galois action. This is four-dimensional quadratic space over F, because you take a norm, reduce the norm, then of course norm of B, iota is norm of B is equal to norm of B sigma, so it is in F. And this is four-dimensional quadratic space with this reduced norm. And so out of that, so you pick a cusp form. F, say weight 2. Now it is on GL to F over GL to FA. And again, weight 2 and homomorphic discrete series. And I would take homomorphic or anti-homomorphic form of lowest weight. Okay, so then I make a theta lift using this space. I choose some short Wurfer function on this diagonalization and bring it to F. And then I want to compute over SHD. Then I get, if you choose phi well, basically L1 of adjoint three-dimensional representation of rho pi, rho f, I would say, two-dimensional representation adjoint of this Galois representation, tensor quadratic residue symbol. And there's a non-zero factor there, something like mass factor of ZL Shimura, and also some finite remaining Euler factor there, but it doesn't vanish. And this is abscissa of convergence, and therefore this is non-zero. Therefore, this is non-trivial in this homology group. That's the first thing. Then I pick now F from now S2 of, so this is, of course, this is a weight 2 on B cross. So this is a Doi-Naganuma lift of a phase change lift, later generalized by a lot of people, but this is the original Doi-Naganuma thing. And weight 2, and so the theta upper sum phi f. This guy is So you take, on the other hand, now space of S2, but S2, but SHB cusp form, holomorphic discrete series, weight 2, and you take a joint, I put lower star, it's a descent, another phi, this phi and this phi may be different, of this F, and then this is actually having a Fourier expansion of something like integral over SH alpha of F q to the norm alpha. I like to write a Q expansion like that. This is Shimura subvariety, something similar to SHD, but this alpha is little differently constructed. So you pick alpha, say in the sigma, and you have original action V goes to V sigma, V in D, right? Then you twist it, alpha V sigma, alpha inverse, and then you can easily check this is order 2 involution. And this action I would call V sigma alpha. And then you take B and the invariant of this sigma alpha, then you get another quaternion algebra inside B for each element of this sigma. And Fourier coefficient is essentially, actually I should have said phi alpha there, finite part. And by that things that at least this kind of cocycle cycles spans one-dimensional non-trivial things in this. So you can project it down to H2R, say over H0 over some number field, H2R of SHB. Oh, I can just say HR of big pi twisted R times contains this class SH alpha and often non-zero. Because it's a Fourier expansion, so mostly non-zero. That's in this kind of way I try to understand the Tate conjecture. Okay? So why this kind of L-value formula comes in, and it's a sort of seesaw principle, but before people call seesaw principle algebra J, the idea that you have any quadratic space B and quadratic form Q over, say, F, and you split it in W, elect some W pop, and then the theta function of Schwarzbrucher function of this space V, if you choose phi to be the tensor product of these two components, then it is essentially phi W tensor theta phi W plus. May not be one factor, maybe a sum, but anyway, something like that. So you can split theta series this way, and once you split it, so suppose this guy has Shimura variety S, this guy has Shimura variety S pop, and this guy has Shimura variety SH, then you know you integrate over S times S pop of X. X is, oh, this is wrong. This is wrong. I started from custom GL to GF, so the X is X. Actually, I do it for SL, but essentially, but that's why you get adjoint. But anyway, so this X is a Hilbert modular variety, and this F tau, tau is a variable of X, Hilbert modular variable, and theta phi is a two variable function. H is an orthogonal variable, I mean variable of B. And then you get the mu, dh, appropriate Haar measure, the mu this side. Then you get an integration over x, f tau, and you interchange s pop, theta phi pop, h pop, dh pop, integration s, theta phi, w pop. I just write w, and this is pop. This is phi pop. Okay? Then you get d tau h dh, something like that, and then at the end you have the mu tau. And then you invoke the zero value formula, you get the basically x f tau of Eisenstein series related to f pop, Eisenstein series related to IW, something like that, mu, and by Rankin-Selberg, it is L value. So what I take for this decomposition, I take the sigma to be the central part. It's a scalar, one-dimensional, and trace zero part. This is a ternary quadratic space. This is one-dimensional thing. And if you do this, so I take this guy to be Z, this guy to be W, not W, E naught. Then this is just a sort of usual stupid theta series. If F is Q, Q to the n square of some perhaps n to the j of some character chi n, and minus infinity to infinity kind of things. No real Eisenstein will show up. And this is a cusp form. This is a matching Eisenstein series. And the very old result of Shimura tells you that is the adjoint L value. And although this computation is not as easy, because this, first of all, you can't split in this way. It's a sum. And you need to make it one piece just so that all the bad guy Eisenstein series vanishes. And in that way, you need to do something. But this is the way, this formula you get. It's not a curve, similar variety. X, why X? Because I lifted Hilbert modular cusp form to B. B is a Clifford algebra, even Clifford algebra essentially, of this D sigma. So F lives in this X, this round F lives in SHB, cusp form of B. This is something strange. This is SHD, right. This one has to be X. Yeah, sorry. I'm under quite a jet lag and I'm so sleepy. Anyway, even though I'm not sleepy, I make a lot of errors. So please tell me if I make an error. Perhaps my lecture is good because I'm so sleepy, it's slow. That's how I make this kind of thing. Okay? And I don't go into the computation of this kind of formula, but this kind of formula you can do for any quadratic extension. You pick any number field and take a quadratic extension, do the same, and you get something, the same sort of formula you get. All the time you get adjoint and variety. And therefore, Tate conjecture is, of course, stated for algebraic varieties. But if you choose, for example, SHD to be algebraic, okay, but you choose E to be non-totally real, then you find some algebraic cycles in the strange cohomology groups, and you can possibly compute its span. So that's Tate conjecture perhaps has some automorphic analog, not necessarily for the algebraic varieties. Okay? So now I just go back to the state cycles. And so you know, I have this E, so I just write H to be the Galois group of Q bar over E. And I define H prime to be, so whatever quaternion algebra a Q you have, then I write I lower Q. This is a set of Archimedean places. So it's a Archimedean places. At that, this Q, new completion is isomorphic to M2 matrix algebra. I upper Q is the complement, so it's Q new is Hamilton. Then this is something you know new. I extended this. I regard this new to the embedding of new of say for example E to Q bar, but this I extend new to automorphism of Q bar, maybe Galois group of absolute Galois group of Q. And in this sense, I multiply this set IB, then you get another embedding, and it fixes this IB. And this is a stabilizer of this set. Then this is defined the reflex field. B. But because B is a scalar extension of D, so it is also a reflex field for D. So the Shimura variety is canonically defined in this round E. This E could be bigger than E, or this E could be smaller than E, possible. And E can be F also, but I rather like to have this situation for simplicity. It gets messy otherwise. And I assume that this big E over E is Galois hypothesis. So whatever you pick a two totally real field, smaller one is Galois inside E. And then you regard this Galois group, E over E, as a isom of E into real number. Then you pick a quaternion algebra. This is just IB. Okay? Then you have actually, you can assume that Galois group acts IB transitively. And of course, you can have a lot of other choices, but you can make whatever big Shimura variety you get in this kind of way. Okay. So, therefore, this H2R, SHB, QL, let's some small pi, big pi, tensor pi finite, I wrote. So then this action is the Galois group of bar over reflex field. And this is a Hecke action. And what is this module? Lagrange, long ago, 79, I think. I was in Princeton there, and he was very happy. And he sort of computed the Galois action. Although assuming some sort of mod P Shimura variety points, structure of mod P Shimura variety points. And so Lagrange started this business. Then, same assumption, Yoshida. So Lagrange wrote their function of SHP as the products of Lagrange functions. Now Yoshida make it from, you have a Galois representation, so whatever pi you have a two-dimensional representation of pi. Two-dimensional 12-bar coefficient representation, modular representation. That you have over this guy. And also, I just write this rho. Then you have rho nu, tau, to be rho nu inverse tau nu. Nu is in, say, IB. Inner conjugate. You have a data of, so that you have a data of rho nu IP. That's a representation of this guy. Out of that, he sort of made a tensor induction he called. It is, his notation is funny, IB. Induction, tensor induction, H to H prime. There's no inclusion really between them, rho pi, but this is a kind of, Maki made this kind of transfer for additively by direct sum. But Yoshida changed that by tensor product. And in this way, you get a compatible system of Galois representation. On the other hand, that L function is Lagrange L function who Lagrange identified except for finitely many Euler factors, that instantaneously by this very stupid argument, you get all the Euler factors. And on the other hand, Zink and Lyman, Zink really computed by trace formula the representation for almost all primes, and therefore they match. And actually, this pi, of course, this is a trace identity all the time. You need to make a semi-simplification, then this is a tensor induction of Yoshida. Tensor int rho pi morphic. So we know all the Euler factors and so on in this kind of way. And a good point is that Good point is that you restrict, I assumed this kind of condition, okay? So E is bigger than round E. And then this tensor induction thing over this H, over H, it becomes tensor product of row mu IB. Therefore, I work with this. I take X, the number field sufficiently large, and I want to compute how many one-dimensional quotient, one-dimensional sum this has. Caveat is that you don't forget about this semi-simplification. So I give a number using this identity, and then the number is actually upper bound. If it is not semi-simple, the numbers guys are less. Here's a formula. I still have 20 minutes or something, right? Slightly more, perhaps. 15 minutes. Okay. So I have this raw news. This is Galois group to GL2. And then you project down to make a projective representation. And the composite I call P rho nu. I only care about one-dimensional factors, therefore projective enough. And this IB, I decompose J1 partition Jn, at that nu and mu is in the same set if and only if P rho nu is isomorphic to P rho mu. So I give a equivalence relation this kind of way and make a partition. By this way, you can easily compute. The point here is that for this II part, forgetting about P up to characters, it is just so J1, I start from identity embedding and something to a new K. Then you have a law itself. Basically, you have a K amount of the same thing. And then, you know, in all the story of Hermann Bay, or actually ESI Sure, and also Frobenius, they computed, so it is tensor product of the same thing. So symmetric group of this J1 acts on this, and this action, by permuting tensor factors, this action and this action commute. And irreducible representation of this guy gives rise to irreducible factor of this guy. And the multiplicity is exactly this dimension of, this is multiplicity free. So therefore, you have a dimension of that guy is and Sure actually classified the representation of this by Young diagram, and doing this kind of business, I can compute quite easily. Of course, if you want, you can use Shimura's theory of polynomial representation by highest or scalar, highest character, and so on, highest weight character. That you shouldn't do. Then you lose this action of symmetric group. And I believe that symmetric group is actually algebraic action. Okay, so that's the proposition. So I write So I write m pi, start from this pi, automorphic representation, number of one-dimensional factors, characters, constituent of entire tensor induction. Okay? Then answer is, so as I said, I take a semi-simplification. So my number is the upper bound of it. So then number one, m pi is 0 if, this is just an exercise, you can do it once you know this kind of stuff. If Ji has odd number of elements, or at least 1i. Number two, if I is not an automorphic induction, from some quadratic field, but it is weight 2, so it has to be CM field. And if it is not automorphic induction, then you use open image theorem. That's something you generalize from Ken Rivet's work over Q, and then use a lot of Grus's lemmas. You know that this kind of tensor product has quite a big image. And in that way, you can count using this kind of classification thing. And Ji is twice EI for all I, then m pi is product of each equivalence classes binomial number 2EI, EI, minus 2EI, EI minus 1. So it grows quite fast. And this formula is called Fock number formula of Frobenius. Frobenius computed the dimension of reducible guy of this representation explicitly, and this is, in this case, Liang diagram of the representation corresponding is something like that. So EI, EI. And so this is something like that. And third point, if I is an automorphic induction, and of course I need to assume Ji is twice EI or I, then it's slightly more. Number 4. Now I use, up to here, I don't need a, not really assumption I made, but now I use H. So assume H. Then, 2E, that's the definition of Ji is independent of I, first of all, and Ji is, new I is an element in Ji times S, and S is a stabilizer of original P law. Okay? From some quadratic extension of your field E. Above. So you have a E, and there's a K quadratic, and from this quadratic and automorphic induction. And therefore, K is a CM field because it weighs 2. And all right, so I can win if this number is 1 because I know that at least one co-cycle is theorem. Before going into theorem, perhaps I erase. I have already shown this. So if EI is 1, so size is 2, then only one dimensional thing there. Agree? So if this 2E I said 2E, I think, if this is 2, then the S is Galois group of E over subfield F, stabilizer. And suppose that B is D tensor FE. Okay? And there's one stupid condition I need to add. And suppose and 2 split in E over F. The Rallis long ago, 87 or something, wrote a book analyzing this theta lift is 0 or not. There's a local condition and a global condition. He listed all local conditions and global conditions. Global condition, okay, because the doubling method tells you adjoint L value again shows up. So therefore, it is non-zero. The local condition, except for 2, you can verify it. At 2, I don't know whether it is known or not, but it's an existence of physical model of SL2 irreducible automorphic representation at 2. If it exists, it's okay. But if split, then the situation is Jacques-Langlands situation. It splits 2 pieces of E, and therefore you use Jacques-Langlands. So therefore, I need to add this kind of strange condition. Then, so if phi is not an automorphic induction, and X is the extension of E, does not contain EM quadratic extension. Or, so the condition is either phi is not an automorphic induction, or if X is automorphic induction case, this does not contain DCM field. from which you induce. Under this condition, then H node X pi R, X is a finite extension of V, anything like that is okay, is generated by the image of SH alpha. So alpha running through all the sigma, of course I need to assume normal alpha not zero. Actually, one SHD enough, because it's one dimensional. And this is kind of the theorem. And of course, when D produces a Shimura curve, R is 1, it's all the time this condition satisfies any Shimura surface, okay? And one more thing I would mention is that you have E and say F and say E. If you choose quaternion algebra of totally bottom and tensor towards E, then all quadratic extension does involved. And if, for example, this pi here is actually pi epsilon the base change drift, if this is the case, IB is just J1, right? And therefore, the action of SIB is really the automorphism, this is a question, of the motive associated to big pi I. This implies the SIB action, you have SHD non-zero there. This is the entire I only explained from the bottom, but you can start from somewhere else. And then you have a partition, and then each guy has to be, this is a splitting of your motive to each pieces. And if automorphism of this guy, then you win. Entire thing. And this is a explicit description of theta cycles, at least conjecturally. And I still have time? Oh, I have 10 minutes more. Is that correct? So as long as you know this guy is really algebraically acting on your Shimura variety, you win. And in that case, you can actually have so instead of taking E over F, you can take E to be the product of E and F and F. It's a semi-simple extension, but still you can make the sigma and so on. So the pair of two, say SHD is a Shimura curve. This produces SHD is in this case SHD times SHD, right? And so why not? You can make any amount of copy to be SHD to be some R. Then, of course, entire symmetric group of R elements acts. And you apply my argument, pair of two things. Then for this kind of product of curve, Tate conjecture, all right. under this kind of assumptions. So therefore, it's not totally stupid. However, all things proved the Tate conjecture for abelian varieties, and therefore, for single curve, of course, his proof works. For multiple product of curves, I don't know if it works or not. It seems nobody worked it out. But this is purely analytic proof, first of all. Secondly, it's totally explicit proof, and therefore, it's not bad, I think. And there's a lot of other examples you can. I did this dimension one case only, but fourfold kind of things, or products of surface kind of things you do. But perhaps originally it has to be done by 11, so I just stop here. Compatibility of this Lagrange, this is it's not too obvious. It's a messy computation, and it's a Duke Math Journal paper, and a fairly long paper. It's correct. This kind of things, if Japanese mathematician did, it's correct. But hugely messy, actually. Jacques-Lagrange correspondence. Yes, it also gives. But I only computed the adjoint value on the Shimura subvariety. Then I need to do, like what Cloutier did, splitting into quadratic field. So D sigma, or D, Jacques-Lagrange correspondence, JL corresponds to E is F times F case. So the quadratic space you project down to left side, it's just a D and H, as Shimizu did. And also you can do this for the sigma thing, but this kind of things, you split in K direct sum K pop for two quadratic extensions. And like what Cloutier did, period integral computation, then you can detect how theta correspondence, or if you use F times F case, Jacques-Lagrange correspondence, how it preserves rationality, either coherent or topological kind of things you can do. And also, as I said, this kind of things you can do for any quadratic extension. So you can do it also for non-holomorphic case also. But it's, I wrote a book on this. It will appear in Cambridge University Press. It's already 458 pages for this Tate conjecture only. So I'm writing for Springer this kind of Jacques-Lagrange or this kind of Doinaga-Numa rationality thing. But if I survive for some time, I think I can do that. Tate conjecture of what? So the Tate conjecture in this type is, as I said, the product of Shimura curves. Curve case you can do. But for higher dimensional case, still not. I think surface products perhaps doable, but I computed a lot of things, but not too much like it. So,